Hello everyone, welcome to the aircraft construction course. I am Zhang Qiyuan. This class allows us to understand the composition of the aircraft hydraulic system. The content of this issue includes basic concept of hydraulic pressure, composition of hydraulic system, hydraulic storage system, system pressurization, hydraulic control system, hydraulic system operation and instruction. Part 1, Hydraulic Basic Concept. The hydraulic transmission uses liquid as the working medium and uses liquid static pressure energy to realize power transmission, also known as volume transmission. The basis is the Pascal principle. The pressure energy on the sealed liquid is equivalent to the transmission in all directions. By increasing the area of action, the output force can be amplified in proportion. The advantages of hydraulic transmission include lightweight, simple structure, convenient maintenance, large output force, fast response, non-polar speed adjustment, and power amplification, so it is widely used in aircraft component drive. Key characteristics of hydraulic transmissions: transferring energy in a liquid in a closed container. The hydraulic pressure depends on the load, external load and flow loss, and the higher the load, the higher the required pressure. Note, the engineering term hydraulic pressure is actually the pressure. The greater the flow, the faster the movement speed of the actuator. The core parameters are pressure, P, and flow, Q, and power is the product of both. The hydraulic pressure of modern civil aviation aircraft has been increased from mainstream 3000 psi, such as B737, to 5000 psi, such as A350, B787. Aviation hydraulic oil has the following index requirements. 1. Stickiness. A1. The fluid moves, it generates internal friction due to the cohesion of the molecule, which appears to be viscous, once called viscous, and a stationary fluid does not show viscosity. 2. Low viscosity leads to seal failure and wear. Too high, it increases resistance and temperature rise. Viscosity is divided into dynamic viscosity, kinematic viscosity, and relative viscosity, such as size viscosity and end viscosity, which need to be measured by a viscosity meter. 2. Chemical stability. Oxidation resistance is crucial. Oil contact with air, moisture or metal, zinc, lead, copper, may oxidize to form acids, resulting in increased viscosity, increased impurities, and component wear. 3. Fire protection characteristics are measured by flash point, the lowest temperature at which combustible steam flashes when encountering fire. Ignition point, a temperature that continues to burn for greater than or equal to 5 seconds. An auto-ignition point, a temperature without fire source auto-ignition. Aviation hydraulic oil needs high fire resistance, such as mineral-based NIL-H5606 flash point 93 to 107 centigrade. Synthetic base BMS 3-11. Flash point reaches 254 centigrade. 4. Compressibility of oil itself is difficult to compress, but mixing bubbles will significantly increase the compressibility and cause transmission delays. It is necessary to strictly control the air content. 5. Lubricating oil film is formed on the friction surface to reduce wear, and the hydraulic oil needs to have good lubrication. Common hydraulic oil types. Aviation plant-based hydraulic oil, for example, MIL-H-7644, blue, containing castor oil and alcohol, flammable, used in early aircraft. Aviation mineral-based hydraulic oil, such as MIL-H5606, red oil refining, used for landing gear, shock strut, etc. Phosphate ester-based hydraulic oil, such as BMS 3-11, purple, synthetic non-petroleum based. Excellent fire resistance, spraying on high temperature flames, only occasionally flashes, used in modern passenger aircraft main systems, such as B737 NG A320. The precautions for using hydraulic oil are: 1. Prohibit mixing. Prohibit mixing oil and drain oil immediately and flush the system if the wrong oil is added. 2. Maintain the necessary cleanliness of the oil and thoroughly clean it when adding oil filter and changing oil. 3. Prevent the system from entering the air. Ensure sealing exhaust after maintenance and maintain normal oil volume. 4. Avoid contaminating other systems and aircraft structures with hydraulic oil and wash with soapy water immediately after oil splash. 5. Protection of maintenance personnel. Toxicity of phosphate ester-based hydraulic oils, irritation due to contact with skin, eyes. Protective paste, oil-resistant gloves, and goggles during maintenance. Clean skin contact with clean water, soapy water, and immediately wash eye contact with eye washing equipment and seek medical treatment. Part 2. Composition of hydraulic system. The cycling process of the hydraulic system of a modern aircraft is hydraulic oil is supplied to the user after the pressure is raised from the fuel tank through the pressurized component and returns to the fuel tank after completion. Systems typically consist of multiple independent hydraulic systems to improve flight safety margins. Aircraft hydraulic system components can be divided into 1. Essential storage components, primarily the hydraulic tank. 2. Booster components. Hydraulic pumps include EDP engine-driven pump, EMDP electric motor-driven pump, ADP air-driven pump, and PTU power transfer unit. 3. Distribution components, pressure return components, piping. 4. Actuator. Actuator, hydraulic, motor, hydraulic, energy to mechanical energy. 5. Auxiliary components, accumulator, oil filter, seal. 6. Control indication components, control valve, cockpit panel. Now let's take the Airbus A320 aircraft as an example to understand the composition of the hydraulic system of a typical civil aviation aircraft. The Airbus A320 is equipped with 3 independent systems of green, blue, yellow, and the main components include 3 hydraulic fuel tanks, 2 fire alarm shutoff valves, 2 EDPs, green/yellow system, 2 EMDP, yellow/blue system, 1 PTU two-way transmission power between green-yellow system, 1 RAT emergency blue system pressurization, 1 hand pump cargo door. Let's take a look at the functions and workings of the auxiliary and executive components. First are the auxiliary components. 1. Oil filter. Oil filter is used to filter impurities in the oil liquid and maintain the cleanliness of the hydraulic oil. It has bypass valves, blockage indicators, and self-sealing valves inside, improving work reliability and maintenance convenience. 2. Accumulator. The accumulator is used to maintain the system pressure, slow down the pressure pulsation, and assist the hydraulic pump in supplying oil. Its inner part is 2 chambers of hydraulic oil and nitrogen, commonly piston, film, and capsule. 3. Sealing device. Sealing device is used to prevent hydraulic oil leakage, and it is common to have an O-shaped sealing ring. 4. Radiator. Radiators are used to cool hydraulic oil. Common ones are liquid-cooled and air-cooled, using aircraft fuel and ram air as cooling media respectively. Shown in the figure is the A-system radiator of the Boeing 737NG aircraft, which is located in the left wing fuel tank. Let's take a look at the execution parts. 1. Single action actuator. The piston of the single action actuator can only move in one direction under the action of hydraulic pressure and is often used in aircraft braking systems. 2. Double action actuator. Double action actuator can use oil to push components to reciprocate and is often used in aircraft landing gear and flight control systems. Gear rack type actuator. The gear rack type actuator changes the linear reciprocating movement of the piston into the rotation of the gear and is often used in the front wheel turning system of the aircraft. Part 3. Hydraulic storage system. Hydraulic storage system components are mainly aircraft hydraulic fuel tanks. Hydraulic tanks are typically cylindrical, fully sealed metal tanks. There are usually 2 types of fuel tanks: bleed air pressurized fuel tanks and self-pressurized fuel tanks. The upper part of the bleed air booster tank is pressurized air, and the lower part is hydraulic oil. The main function of the fuel tank is to store hydraulic oil and leave enough space to ensure the expansion of hydraulic oil. The change in oil volume is caused by the temperature increase and thermal expansion during the operation of the hydraulic oil. In addition, the hydraulic oil tank also has the functions of heat dissipation, separation of air in the oil liquid, and precipitation of impurities in the oil liquid. The self-pressurizing oil tank is a high-pressure oil supplied by a hydraulic pump that acts on the piston of the tank and pressurizes the hydraulic oil in the tank. The amount of boost pressure depends on the area ratio of the two pistons. Let's meet the fuel tank exterior. Components. 1. The engine drive pump oil supply port and the electric pump oil supply port. 3. These are crucial points for the system's operation, ensuring proper lubrication and function. Return port. The system return oil is returned to the hydraulic tank through the return line and the return port. Usually, the oil return port is located in the middle of the fuel tank, which is conducive to the system oil return and the hydraulic oil inside the fuel tank to be fully mixed and cool down quickly. At the same time, it can also prevent the oil return from lifting the impurity at the bottom of the fuel tank and sucking in the pressurized drive pump through the oil supply port. 4. Oil discharge valve. Drain the oil tank. Regularly collect oil samples inside the hydraulic tank. Conduct laboratory analysis and detect impurities, moisture, particulate matter, etc. inside the oil tank. If it is found to exceed the standard, it is necessary to update the hydraulic oil in the system. 5. Oil gauge. Check the amount of hydraulic oil inside the tank during ground maintenance. 6. Oil amount sensor. Detects the amount of hydraulic oil in the hydraulic oil tank and provides hydraulic oil AMSI data to the cockpit and computer, or issues a low oil amount warning. The hydraulic pump is the power source of the hydraulic system, all of which are volumetric pumps, and its working principle is to use volume changes for oil suction and pressure oil. Hydraulic pumps have various classification methods such as gear pumps, vane pumps, and plunger pumps, according to their construction. The high-pressure hydraulic systems all use plunger pumps as power sources. Let's focus on learning how plunger pumps work. The figure below shows the construction of the Boeing 747 aircraft engine drive pump. As shown in the animation on the right, during spindle rotation, the plunger pump relies on the plunger to reciprocate in the cylinder, so that the volume of the sealed working chamber changes to achieve oil suction and pressure. The plunger pump moves to the left during the process from the top to the bottom, sucking hydraulic oil into the chamber. During the process of the plunger pump from the bottom to the top, the plunger moves to the right and presses hydraulic oil out of the chamber. In modern aircraft, engine-driven pumps and electric motors-driven pumps are often used as the main source of boost for the system. The engine drive pump is usually a swash plate plunger pump, which is installed on the accessory gearbox of the aircraft engine. The engine rotor drives the oil pump to operate through the accessory gearbox to pressurize the hydraulic system. An electric motor drive pump, EMDP, is driven by an AC electric motor, and is therefore also referred to as an electric motor pump, EMP, or an AC control pump, ACMP. It is basically similar to the working principle of the engine drive pump, EDP, but the main difference is that the power source of the drive plunger pump is different. The electric motor drive pump is rotated by a drive shaft of the electric motor drive pump. The main function of auxiliary pressurization is to provide backup for the main hydraulic system, which is generally used when the main hydraulic system fails or is maintained on the ground. Common sources of auxiliary pressurization are ram air turbopumps, ram air turbine, ranters, power conversion assemblies, air-driven pumps, and ground hydraulic vehicles. The ram air turbine, RANTEs, can be used to provide emergency hydraulic pressure to actuate the flight control system, while also providing emergency power to the aircraft under normal circumstances. The RANTEs is retracted from the fuselage and can be released automatically or manually when certain conditions are met. The power conversion assembly, PTU, is a combination of a hydraulic motor and a hydraulic pump that uses the pressure of one hydraulic system to drive the hydraulic motor and drive the hydraulic pump to pressurize another hydraulic system. The air drive pump, ADP, is driven by the bleed air of the air source system, mainly composed of shutoff valves, turbines, gearboxes, and hydraulic pumps. The bleed air drives the turbine and drives the rotor of the hydraulic pump through the gearbox to rotate and pressurize. During ground maintenance, ground equipment, hydraulic vehicles can be used to pressurize the hydraulic system and reduce the use of aircraft hydraulic pumps. The ground hydraulic vehicle is connected to the aircraft hydraulic system through high-pressure joints and oil return joints. Hydraulic control system. Hydraulic control elements are used to control and regulate the flow direction, pressure, and flow rate of oil in the hydraulic system, also known as hydraulic control valves. The direction control element is used to control the opening and closing of the oil and to change the direction of the oil, and can be divided into a check valve and a shuttle valve. The main feature of the one-way valve is that oil can only flow in one direction and cannot flow back. Its working principle is that oil enters from the left side, flows to the right side after overcoming the spring force. The directional control valve is used to control the flow direction of oil in the system and can be divided into rotary valve, spool valve, and shuttle valve. The shuttle valve controls the change of the oil pass by rotating, sliding, and hydraulic pressure changes. Pressure control elements are used to adjust or limit system pressure. Common pressure control components on aircraft include relief valves, pressure relief valves, priority valves, etc. The spill valve maintains the pressure of the system constant through the spill action of the valve port, which is divided into two types, direct action and pilot action. The direct acting relief valve has a simple structure and low pressure regulating accuracy. The pilot relief valve has high pressure regulation accuracy and is suitable for high pressure and large flow systems. The pressure relief valve is used for pressure regulation in a single boost source system and is divided into a constant pressure relief valve and a constant difference relief valve. The control pressure of the constant pressure reducing valve comes from the outlet pressure, and the valve port is normally open. The opening degree of the constant difference pressure reduction valve is only adjusted by the inlet and outlet pressure differences, and the inlet and outlet pressure differences are kept constant. The priority valve is installed downstream of the important component. When the system pressure is insufficient, the oil supply to the secondary component downstream of the valve is cut off to ensure that the important component is preferentially supplied with pressure. A flow control element, referred to as a flow valve, functions to regulate and control the flow of liquid in a hydraulic system line to regulate and control the speed of movement of an actuator. Common flow valves on aircraft have throttle valves and hydraulic insurance. The throttle valve uses the principle of small orifice throttle, which produces a pressure difference when oil flows through the orifice, and plays the role of pressure reduction throttle. Hydraulic insurance serves as a safety device to prevent all oil in the system from leaking when downstream components or pipelines are damaged. When the flow rate increases to the critical value, the hydraulic insurance closes the oil outlet. In the hydraulic system, the high-pressure oil at the outlet of the hydraulic pump is distributed to each pressure system through the pressure components, and the oil from each subsystem is returned to the oil tank through the oil return components. The pressure component is installed in the outlet pipe of the hydraulic pump, and its main function is to filter and distribute high-pressure oil to each pressure system. The interior includes check valves, oil filters, relief valves, pressure sensors, pressure switches, and the like. The oil return component is installed in the oil return pipe, and its main function is to filter and guide the oil return to the oil tank. This interior includes components such as oil filter, bypass valve, and check valve. hydraulic system operation and instruction. The crew or maintenance personnel can control the work of the corresponding hydraulic system through the cockpit hydraulic panel. Sensors and switches in the system detect the operating status of the system, are used for cockpit indications and warn when the system is operating abnormally. According to the priority used, the hydraulic pump is divided into the main pump, the backup pump, and the emergency pump. The main pump is always in operation. The backup pump is controlled by the unit, and the emergency pump is mainly the ram air turbine (RAT). The hydraulic control panel is used to control the operation of the hydraulic system, including the main pump, the backup pump, and the control switch of the emergency pump. As shown, the hydraulic control panel is generally located on top of the cockpit. The hydraulic indicator system mainly provides the unit with parameter indicators such as oil quantity and system pressure, and warning information such as low pressure of the hydraulic pump and over temperature of the oil and electric motor driven pump. The figure shows that the oil value Q of the hydraulic systems of the B737 aircraft A and B is 100% of the full oil amount, and the pressure value P is about 2,800 psi. The oil level sensor in the fuel tank uses the float to feel the change in oil level and displays the oil level on the oil meter and cockpit panel or display outside the fuel tank. Pressure sensors detect continuous pressure signals and are typically used for cockpit displays. A pressure switch is typically used to trigger a system low pressure warning, lighting a warning lamp or warning message when the detected pressure is below a certain value. The temperature signal of the oil and electric motor hydraulic pump is detected by an over temperature switch or temperature sensor, and a warning light or warning message is lit when the temperature exceeds a certain value. This course is over. Thank you for your study. Now comes the exercise session. Students can press the pause button to think and answer. Let's start now. Have all the students answered correctly?